Hello everyone. Can you hear me clearly? Hello everyone. Can you hear me clearly? Great. So everyone can hear me and let's start the session. We are already running 2 minutes late. Actually, many people are trying to join. That is why. Hi Kumar. Hi Mark. Hi Teher. Hi Mrin Moedas. Hello Suresh. Hello Rakshit. Hi Johnny. Hello Mohan. Hi Ravi. Hi Paramesh. All right. So it'll be great if you start with your introduction before we start the session so that we know about our audience today. Hello, Mohan. All right. So the way these sessions happen is because there are many people in the session. I have everybody is muted except for myself. Okay. And the way we communicate is you type your question and ask, and then I read it out for all. Okay. So hi Rakshit. Rakshit is a product manager at McKinsey. Nice to have you in the session, Rakshit. Great. We have business analyst SAP, Suresh. Great. All right. So let's start before further delay. So first of all, welcome to Big Data and Hadoop first session. This is session one of our 11 sessions. Okay. And a little bit about the instructions for this session. The session is being recorded and the recorded video will be shared with all of you. The presentation also will be shared with all of you. And since this is an open free sessions for all, okay, I mean, there are students also who have enrolled for the class. There are people who are attending it for free also in the session. Okay. And those who are our students in the session, they will have all of the recorded videos as well as the presentation available in their LMS. For rest, I will be emailing the video and presentation. All right. So get yourself comfortable in asking the question by using the questions window. All right. A little bit about no big data is the unique proposition with respect to no big data is we are trying to have the best instructors in the industry, and we have something called cloud labs using which the users can practice online itself using multiple computers rather than a single virtual machine. And we provide a lifetime access to the learning management system where you will have all the content for learning the technology. Okay. At the end of the session, we provide you a real life project. Okay. So generally there are two projects. One is a mandatory project at the end of the project, at the end of the session number 11. That mandatory project is a simple one. Those who perform really good in that project and have finished all the assignment, we involve them with a real life project. Okay. At the end of session, we provide you a course completion certificate, and it's fairly our certificate is fairly accepted in the industry. Okay. Other than providing a 24 by 7 support, we proud make sell we take pride in having our great alumni connected together. And by having alumni, meaning we basically share the jobs with them, we keep them informed about new technologies, and if they face any kind of challenges, they generally write to us. All right. So we try our best to keep a great, vibrant alumni. All right. A little bit about myself. I'm Sandeep Giri. I did my graduation 2002 from IIT Roorkee. Afterwards, I worked in a company called DE Shaw. DE Shaw was the place where my career started with handling a lot of data. At that time in 2002, we had a cluster of 10,000 node. We used to call it grid. And that time we were handling data in terabytes. All right. Afterwards, I founded a company called T-Bits Global, which I ran for 6 years. And there I built along with the team a document management system which is similar to what we have MongoDB as of today. And afterwards I worked at InMobi where I built a recommender and I built some layer on top of Cassandra. And afterwards I worked with Amazon where I was working on something like Apache Storm for optimizing the images. And then in April 2014, I thought of starting the No Big Data along with a couple of my friends. So that's about me. Let me read a little bit about you. So we have Kumar Saurabh, who is an engineering manager at GE. Great to have you, Kumar Saurabh, in the session. Hi, Parmesh. Parmesh is a software engineer. We have Eric Diana. She's a he's a solution architect. .NET development and architecture for 15 years. Great, Eric. And we have Mirin Moy. Currently, is working as a Ruby developer at a startup, and he's here for out of curiosity. I don't know. I don't have many experience in the field. Hoping to get a premiere on the Hadoop. Okay, so great. You are at the right place because this is going to be a simple introduction today, which should be sufficient for you to decide and understand whether this technology or this domain is good for you or not. All right. So we have Mark Penn. Mark is a software engineer and he's also new to the field. Okay. So everybody is mostly new to the field. It has been hardly 3 years, since 3 to 4 years since the technology came to production. We have Ravi Krishnamurthy, who is also engineering manager. Great. So Tahir is working as data stage developer. So Tahir, mic will not work for you. Okay, that has been muted, so nothing to worry. Everybody has to type and then ask the question. Okay. All right, so let's jump in. Today we will talk about uh, what is big data, how do you classify, and how do you, uh, you know, handle big data. What are the various technologies available? Why do we need to handle the big data, and what are the problems associated with it? Along with that, we will talk about Hadoop HDFS architecture. All right. And then we will open for the questions. All right. And keep on asking the questions. Do not wait for me to stop. All right. Keep on asking question. I will answer the question as soon as I finish explaining a particular topic. All right? Sounds good to you? Great. Now moving on. So before going further, let me ask you, what is it that you understand by big data? There seems to be a lot of confusion around what is big data itself. And every blog here and there, they all start with defining the term, and only few are able to successfully convey the meaning of big data. Okay, lots of data, perfect. That is Parmesh. All right, generated by IoT. So, Parmesh, the data could be generated by anything, not only IoT. IoT is Internet of Things, and it's just another term for saying lot of devices are generating data. Rakshit is saying volume, velocity, and variety. Good, good. All right. Suresh is saying data hues volume. Good. Big data includes what is available outside internal company, such as data from internet. That's Johnny. Okay. And yeah. So that not necessarily. Okay. Big data can be from anywhere. Gathering our information to dive into to review and resolve questions. So that is Mark. So Mark, that's anyway the objective of any data analysis. All right. Very good questions. Very good answers. Go ahead. Providing value based on the needs from volume, velocity, and variety. Okay. So yeah, that's a political answer based on what IBM has been doing. But good, but good. All right. So different types of data: numerical, text, images, video. That is Kumar Saurabh. Anybody else? All right. Great answers. Great set of answers. All right. Now let's start with my our definition. Okay. So in very simple words, big data is nothing but data of very big size. Big data does not mean data analysis. Big data does not mean data gathering. Big data is a noun. Big is an adjective. Data is a noun. We call big data that says that we are talking about, you know, so big is an adjective and data is an object. And big data essentially means data of very huge size, as simple as that. Let's not confuse with anything. All right. Now, how big the data should be to classify it as big data? In very, very simple words, the moment you realize that you cannot process the data using a single computer, you might require multiple computers to solve your problems, either with respect to storage or processing. Then you say that my data is big data. Okay? Let me repeat. The data which cannot be processed using your usual tools, for which you require a distributed computing. Okay? Then you call the data as big data. All right? That's a definition, and we will stick to this definition all throughout. All right? So at the moment, so when you're dealing with a certain amount of data, and to store or process that data, you realize that you cannot live without doing it using multiple computers. Single computer is not sufficing. Then you call that your problem is a big data problem, and the kind of data you are dealing with is big data. Sounds good to you? That's a thumb rule, okay? That's a real definition of big data. And whenever you have to judge and whenever you say that, okay, I'm talking about big data, this is the general thumb rule. All right. But when people ask you, this is the general definition people have been popularizing, although it does not make much of a difference, but it is good to know this definition. So these are four characteristics of big data. These are the four characteristics of any data that might make the data so big that you have to consider it for distributed computing. So your data can have a huge volume, or it is being it is moving at a very faster rate, or it has various kinds of variety. And because of any of these characteristics, you might end up using a distributed computing environment. You might end up using multiple computers, okay? And that's when you call your data as big data. All right, what kind of volume are we talking about? So volume means the data at rest, the data in your storage. All right. So, for example, every day Facebook gathers 500 terabyte of data. Okay. These are just examples. All right. Similarly, we have velocity. Velocity means the data being gathered or data being transmitted at a very faster pace, and lots of data is being transmitted. All right. So, for example, if in this session there are 50 people, and I'm sending a audio video from my side, and it is being sent to all of you at the same time. From the server point of view, there are 50 connections. Okay. And every second or every millisecond, the data has to be distributed immediately to 50 people. Okay. So that is velocity. Or you can think of it this way, that on Facebook, lot of data is being generated every day. That is data at data at rest. Every day the data gets into rest. And at the same time, there are so many people connected to the Facebook, and all of them either are posting their status or asking the Facebook to give the fresh feed. Okay, because of which there is a huge volume, huge velocity, huge number of requests that are going to the server and leading to the velocity. Okay, there are various cases when there is a huge velocity but there is no volume. For example, a website counter. If there is a website counter and this website has got many hits per day, and this counter is being used by hundreds of websites, and in that case, even though at the end of day this stat counter, the website hits counter, is only storing 100 numbers, okay, the volume is too low. But if the hits are coming in thousands per second, then that means there's a huge velocity but a low volume. Okay, so that's the definition of velocity. So due to velocity, you might end up using a distributed architecture for handling the load. Facebook or maybe a small service, they have many users concurrently. There are many users concurrently using a service. You might have to use a distributed environment to handle that many users. Okay, and that's when you call your data as big data. Third is variety. Variety means by virtue of different kind of data, your processing becomes complex. And because of the complexity of your problem, you realize that your single computer cannot solve the problem and you need a distributed architecture. That's when you call your data is big data because it has got variety. Okay, let's take a case of a map problem. Okay, imagine there is a you are provided with the whole country's maps. Okay, whole country's maps, and the maps could be in various kinds of format. It'll be a complex format having multiple layers of information, and analyzing a map requires many kind of algorithms which are inherently complex. So say you have to find the route from one place to another, shortest route from one place to another in a country's map. Okay, and you have to do it really fast. In that case, just because your data is, even though the maps may be say 100 200 GB or maybe 300 GB, even though the volume is not big, still, because of the nature of the problem, because of the variety of data, you end up using multitude of computers using multitude of computers to solve this kind of problem of finding the route on a map. Okay, the third one is veracity. Veracity is, you know, I find it very strange, but it has been introduced anyway by IBM, and every year they have been introducing one more V in the definition. Probably they have added value last year, and this year they might be planning some more V's in this definition. But nevertheless, I'll try my best to explain to you what does it mean by veracity. So there are situations when you do not know. There are situations when you do not know whether to drop the data or keep the data. All right. Let's take an example of temperature data. You have got five different sources from which you have gathered temperature data. One source gave you the data containing the temperature readings, which is per hour, but is but it has a GPS location along with this. So for each GPS coordinates, we are given the temperature data. Second one gives you the data based on zip code, but the temperature data is per minute basis, not per hour as in the first case. Now third case, you get you got the data from a little unreliable source, but it is very fine grained one. It has got GPS coordinates and it has got the temperature reading per minute. All right. Now you have got three different sources of data. To reach to a conclusion that which data set is more reliable, you will have to do a processing of all three data sets. Now, just by virtue of this doubtfulness, just by virtue of this doubtfulness, we have three data sets, which means our total data demand has become three times. Okay, and by because of these kind of confusions and doubts, you might end up having a storage or a situation where you have your your demand has increased multiple times, and therefore you require more volume, more space, and due to which you have mm, your volume demand becomes so high that you have to have a distributed environment for the storage. All right, that is how veracity leads to a big data problem. All right. So let me read out Mark's question. When creating web application using this technology, do you recommend multi-threaded connections like Java, or can single node with sublayering with Node.js actually handle it? So no matter what technology you use, most of these problems cannot be handled with a single computer. Okay, and we will talk about this in detail. All right. So Rakshit, what was your point? Yeah, about veracity, it's actually the way they have coined a new word, to be honest with you, and it actually lies in the domain of variety in volume, as you have correctly pointed out. Okay, so you can say that it's a new kind of a variety of data, which is due to general confusion whether to keep a data or drop a data, or it's a half processed data, because of which you might end up having a volume. So you are correct in that way. All right. All right. So before we move further, just to check if you are awake and with me, I have a question to ask. How many bytes are there in a petabyte? Quickly. All right. So Rakshit says 1,000 terabytes. Suresh says, hmm, I don't know how many zeros are there. All right. All right. So good. All right. So almost all of you are correct. So in very simple words, petabyte is 15 zeros. Okay. Petabyte is 15 zeros. Those who have Googled in the meantime would get this answer, what I've written here. All right. So in the way you should remember it is in this manner: kilo, mega, giga, tera, peta. And everyone is a 1024 multiple of the previous one. So it's a 1024 multiplier table. A kilobyte is 1024 bytes, mega is 1024 kilobytes, and so on. Okay. Every time three zeros are added. All right. Just let me turn off my phone. All right. So, all right. Now, this is the question I want to pose to you. It's a difficult question. Is one petabyte data? In previous one, we said there are 15 zeros in a petabyte. Okay. In your opinion, do you think one petabyte is a big data? We talked about big data. Big data is simply a data for handling and processing of which you require multitude of computers. Okay. And a petabyte is 10 to the power 15, 1,000 terabyte of data. Now, do you think 1 petabyte is a big data? All right. Okay. So, the what is the minimum thing you would like to do with the data? Minimum thing. Storage, right? So let's take a case of storage. If you have to storage 1 petabyte reliably and have to access it uh, also in a reliable manner, access minimum amount of work. Say you have to compute, just have to sort the data. 1 petabyte data you have got, you just have to order this data. Okay. So can you do it using a single machine? O- Okay, and that too, I mean, reasonably, in a reasonable amount of time. So Paramesh says no, Johnny says not necessarily, depends on the characteristics. Rakshit says depends on how fast I want the output. That's a very good point. So let's say we want a reasonable answer, as in if we want to sort this data, we should be able to sort this data in say in maybe say 6 hours, or we should be able to access particular information in a reasonable amount of time. Mark says it depends on how much of it you need. So let's say I might need a needle from this whole haystack. All right. Yes. So Rajiv, my question is, Rajiv's point is if it can be handled by one computer, then it's not very correct. So my question to you is, do you think it can be handled by one computer? Okay. Ravi says that these days the hard disk is around teradata, right? So if it's a terabyte, so which means you'll require 1,000 hard disks. Kumar says that yes, because I can't process that much data on a single computer. Right. Mark says probably not. Eric says no. And yes, machine, Johnny, by machine, I mean the single server. Parmesh says that then I think we need more processing power. Okay, so that's a very good point. I'll come back to that. That is not only the processing power which is the bottleneck. When we say computing, computing does not mean the processing power. We'll talk about this. All right. So my answer is that if you have to, so although every question can be answered with it depends, with a single phrase called it depends, but let me put a very concrete way to it. Okay, so in my understanding, big data, a 1 petabyte data is a big data for multiple reasons. First, to get to reasonably store it, to store this kind of a data, you cannot do it using one computer. Okay, even if you did, then accessing this kind of data would be extremely slow. Second, if you have to do even a minimal amount of processing, if you have to do a basic amount of searching in this data, you cannot do it using a single computer. All right? You might even if you have to prepare a simple index, that will take a lot of time for a single computer. All right? When I say index, index means if you have dealt with the databases, or even if you have used a dictionary or a book, at the end of the book you have this index which help you find which word you are looking for. So even preparing that index out of 1 petabyte data will take a humongous amount of time. Yes, Eric is right. The IO limitation is something which we all overlook. We have been always thinking in terms of processor, in terms of processor. But processor is no longer a bottleneck. All right. We'll talk about this after this slide. So a little bit brief history about data. So there are people who actually count how much digital storage is being sold to various people around the world. Okay. And based on that, it is computed that the digital it is computed that how much digital storage is being used by the world. And in this graph, the most important part is first, analog storage has not expanded. Digital storage suddenly started increasing exponentially and in 2002, and that is why we call 2002 as beginning of the digital age or digital era. Lots of and there was a very simple reasoning. There was a very simple reasoning why it happened that way. Okay. The answer is device and connectivity. Device and connectivity. While on one hand, devices became cheaper, faster, and smaller, on the other hand, the connectivity became more and more available and more faster. Everybody started having 2G, then 3G, now 4G, and their Wi-Fi all around. So basically, the while on one hand the devices produce the data, connectivity multiplies the data. Okay, connectivity multiplies the data. So and because of the devices and connectivity, the hardware layer, software automatically had to evolve in order to provide the best user experience, to put both these things into use. And so there are a lot of software which came up, Google Plus, Yahoo, YouTube, Twitter, this, that, to propagate the information around the world. Okay. So basically, this is the reason why 2002 it was a critical point in the history. Both the sides, the devices became cheaper and cheaper every day, smartphones specifically, and then connectivity became popular. There were new modes of communication. All right. So these are the reason why the data became so high. The data need became so high from any of the backends, any of the servers. The data requirement became high, and that's when the big data need actually became very prominent. The need of handling big data became very prominent because of these factors. All right. Now, why does a big data problem? Okay. Earlier, before 2000s, we had a simple answer. We will have a better processor in 6 months. Okay. Every 6 months, processor was doubling. Now, even if you double the processor, it's not going to help. Reason being, Reason being, processor is no longer the bottleneck. The bottlenecks are other parts. Your RAM is a bottleneck, the disk speed is a bottleneck, the IO is a bottleneck. And when the disk size becomes the problem, we move the data to the network becomes the problem. All right? So, it's not only the CPU that's a pillar of the computing. It's all of these four things which are pillar of computing. And whenever we say a computer can do fast, it can perform things faster, all of these four things have to be faster. All right. And when it comes to big data, at least one of these things become bottleneck, either the CPU or RAM or network or the disk. Any of the four would become the bottleneck. Imagine that you have got you have just launched a website. You've just launched a website and lots of people are hitting your website. So first thing you will do is the first thing that would be making you slow is your reads from the database. So what will you do is you will read this data from the disk and put it into the memory. Okay. So the memory suddenly becomes your constraint. Okay. The only way, one way to increase the memory is add more and more um, memory stick to the computer, but that has got a limitation. A CPU can only handle up to a certain amount of memory. Second is, and when you have too much of memory, only then your CPU will become the bottleneck. But before the CPU becomes the bottleneck, the network bandwidth of that computer, which is serving so many requests, will become the bottleneck before before CPU becomes the bottleneck. Okay, and this is the story about Wikipedia. The servers of Wikipedia actually got the similar kind of a bottleneck. All right. Now, before the CPU became the bottleneck, first your disk became the bottleneck. You tried to move that bottleneck towards RAM, and RAM also hit sort of a bottleneck at a certain point of time, and that was due to CPU or the network. All right. So this way, all these four things are so well connected that at least one of them, I mean, all these four things matter a lot when we talk about computing. And and at a lot of time you will realize that just buying a new computer, just buying a new machine or a new server, attaching it to the network does not only double the speed, or does not only uh, it actually gives you more than twice of performance, because all of these four components will get doubled the moment you get a machine. You'll get a new CPU, you get a new RAM, you got a new network, bigger bandwidth, and so on. Okay, that is why even if you have a supercomputer, still it will not be any helpful. And that is why a distributed computing is the only way to solve most of your problems related to big data. When the data keeps on growing, or in any way, say number of requests are growing per minute, you cannot solve it in any other way than having multiple computers. All right. So so out of these four pillars of computing, at least one of these will become the bottleneck. And that's why we need to learn the new paradigms of computing. All the tools and the product which we will discuss in this course of big data and Hadoop, they all run parallelly on multiple computers. All right. Make sense to you? Any questions still here, or so no questions? I'm assuming either i did not say I did not explain well, or okay. So Mark's question is, uh, yeah, all right. So I missed. Yeah, okay. He's saying that no, that's how Google got started. Okay. Okay. Aditi's question is, can you please repeat the flow of data access through these four components? Okay, we'll talk about this. All right. So, okay. So you guys are finding my explanations good. I'm happy. So let me explain again once more. So these are the four components inside a computer which matter when you are dealing with any kind of computing. It's not only the processor that matters. Imagine, if you talk about the story of say Wikipedia, more and more requests started coming, and it was harder to serve all these requests in a reasonable time directly from the database. Because when you read something from a database, you are going to read from the hard disk, and reading from the hard disk is fairly slow. Okay, so they started caching lot of data, and when they started caching lot of data, the bottleneck moved from the hard disk to the RAM. After some time, RAM itself has got its own constraint. First, RAM is extremely expensive thing. Second, every computer can only have a certain amount of RAM. Okay. Third, the moment you start increasing the RAM, the other components will start becoming the bottleneck. Say you are able to handle thousands of requests using a computer and a RAM, but your network does not have that kind of bandwidth. Okay, so the network will become the bottleneck. So the bottleneck will keep on shifting from one place to another. And at a point of time, you will realize that there is no other way than having more computers. And also, one more thing I would like to emphasize here, there is a definition thing. There is something called horizontal scaling and vertical scaling. As we said that we will increase the RAM, this is called vertical scaling. As we said that we will increase the CPU, that is vertical scaling. Horizontal scaling is that we buy one more computer, attach it in the network, and let it also serve some of the web pages. Okay, do a sort of a load balancing at the DNS level or anywhere else. Load balancing means sending some of the user load to one computer and some of the user load to another. So so that way, this is the reason at a certain point of time you will realize that no matter what you do, one of it is becoming the bottleneck. A more cheaper way would be to buy a one more machine and put it in the network. Okay, and that's how a big data problem is solved using the distributed computing. Okay, another example to differentiate between vertical scaling and horizontal scaling is, imagine you have a bullock cart. Okay, and it has a single bull right now. If tomorrow your load requirements increase and your single bull is not able to pull the cart, going for an elephant is called vertical scaling. But adding one more bull into the cart is called horizontal scaling. All right. So that's what it is. Now let me go through a simple case study of, so we said first we said few things. First, big data is storing big data and all of this is difficult, and lot of data has been accumulated and all of this. And we also said the reasoning behind it. But what will we do with this kind of data? What will we do with this kind of data, and why do we need to bother about any of this? The reason is very simple. Bigger the data, better the analytics. Bigger the data, better way of better insights you can get. Okay, let me ask you a simple question. Okay, all right, there are two hospitals. Okay, hospital 1 says that we have infants, out of 100 infants on an average, they have 55 girls and 45 boys. Hospital 2 says, or you can say 60 girls and 40 boys out of 100 infants. Okay. Now there is another hospital too in the same city which says that out of 100 infants born, we have 49 girls and 51 boys. Okay. Now what can you say about hospital 1 and hospital 2 based on this data? Anyone? There are two hospitals in the same city. One says, Hospital 1 says that out of 100 infants born, there are 60 girls and 40 boys. Hospital 2 says out of 100 infants born, 49 girls and 51 boys. Okay, Aditi says Hospital 1 has more girl infants than 2. Okay, Rakshit says Hospital 2 has better sex ratio. Can you tell something about which hospital out of these two is older or more popular? If you go to Hospital 1, you may get girl child or more mortality. So can you tell me something about, answer this question. Number of children born in A, A option is hospital 2 is more than hospital 1. B is, okay. So total number of children born in hospital 1 or hospital 2, on which these statistics have been computed, which one do you think is correct out of these two statements? Right, right. So everybody is right, exactly. So we all know as a common wisdom that girl and boy ratio is almost similar, okay, in general. This is a normal city, it's not something different. So the when you look at these numbers, the first thing that you will raise the question is, maybe this hospital 1 is recently opened in past few months and they have hardly completed first 10 infants, first 100 infants, and that is why their information is very skewed. If they run for maybe 2 years, when they have 1,000 infants, they will have a proper statistics. That is why, the bigger the stat number, the better the statistics. Okay, the bigger the number, the better the statistics. All right. So Rakshit, does it make sense to you? His point is that we cannot answer that because we do not have data about time here, right? That is correct, but that's correct partially. But if you look at the way, if you have to answer this question, we know the fact which we are dictating here is, in general, the ratio of girl and boys is very similar. Okay, so based on that premise, we can fairly say that the statistics of hospital A is very skewed. Okay, and if assuming that hospital 1 is not running a fraud, then the only case is the hospital 1 does not have bigger data. Okay, so the point which I have been trying to make, right, that's right, Eric, right. So in general, the bigger the data, the better is the statistics. It's as simple as that. Okay, that's what I have been trying to explain using this particular example. I was taking a reverse way. The better the statistics also mean the better was the data. Okay. Now let's take few example cases. The the biggest example of big data problems, or the way the big data was utilized, was Amazon's recommendations. Okay, or Netflix recommendations. All of these recommendations were based on the historical behavior of lots of people. And Amazon realized that other than their newsletter, recommendation were the second best thing that they did to increase their sales. And if you try to prepare the recommendations based on a very small data, the recommendations are actually very ugly. People, your customers will lose faith in you if you give a recommendation in a which is not based on very big data. Okay, that's why a lot of people end up doing hand curation in the beginning. Okay, which is very biased by the one user or two users. All right. So recommendation is one such case where big data comes into play quite often. So what is recommendation? Based on the history of the users, you try to recommend them something. Okay. So here it's there is one with which says customers who bought this also bought this. Preparing this kind of recommendation is actually very simple. Similarly, in that Netflix or other say IMDb, there are recommendations for you based on which movies you have liked. Okay, so there are many algorithms which have evolved over a past few years to give you the recommendation. It tries to group the users into various buckets and then start giving recommendation from one to another. All right. Now, one such case which we'll discuss in session 9 would be a simple recommendation problem of of uh, of movies. Given given we will basically prepare a three-column Excel sheet, three-column tab separated data, which we will feed to a tool called Mahat. And Mahat has a predefined algorithm with a set of around 11 algorithms from which we will pick up one of the cases, and Mahat will give us the recommendations directly. For this user ID, for this movie ID, this is the rating. So most of the work of building algorithm is generally done by people already. You could utilize it right away. All right. So there are these kind of tools which help you build recommendation very quickly. All right. Now, second big use case which probably everybody is talking about Right, right. That's correct, Mark. Mark says that you would need more exploratory sources to infer the answer, hypothesis, then described, then prescribed, exploratory, leads to inference, then predictive. That's nice, right? All right, so let me talk about another problem which is very prevalent as of today is called sentiment analysis. Okay, using a sentiment analysis. Okay, so Mahat is a collection of algorithm. So Tim is saying that can you go back to the previous slide? What is Mahat? Okay, so Mahat is a collection of algorithms. One of the algorithms it has is for recommendation. Okay, so it does give you recommendation, and recommendations are also called collaborative filtering, and they are also called user to product mappings. Okay, okay. And recommendations come in various form. First, a recommendation based on your history or based on the history of a product, such as people who bought this also bought this. Okay. And your history, you may also like it based on what kind of things you have liked in past. We will give you the very close recommendation. So this is how if you have to build a recommender in couple of hours, probably this is the quickest way of doing it. All right. But the trick would be to prepare the input data in this format. Prepare the input data so that the rating is always between 1 to 5. So that's where the little bit of statistic analysis would come into play. All right. Is it clear, Tim? No? Mahat is a library which takes three column input and gives you the recommendation. This user liked this movie this much. Kumar liked Matrix, and the rating Kumar has given is 4.0. Kumar has also liked Ice Age and it is 3.5. Giri has liked Casablanca and the rating is 3.6. So Giri has also liked As Good as It Gets and at some rating. All right. Based on this, Mahat will prepare the recommendation and Mahat will have no other input than this data. Okay, just based on this it will figure out, so there are say 1 billion such ratings. Mahat will figure out which users are similar in behavior and then start cross recommending, and there are multiple algorithms to do that. All right, so Mark, I did not get your question actually. So your question is data frame as pre-prep or table. So data is in the form of tab separated format for the. All right, let's move on to something called sentiment analysis. You must have been hearing about it. And sentiment analysis is basically understanding the public sentiment towards a particular keyword, a brand, or a personality, or anything. Okay, and how what is public? What are the people talking about it? Are they talking negative or positive? So the representing all of the sentiment as a simple number is what we call sentiment analysis, and drawing it over a period of time and comparing it against another similar brands is something very much required. So the most rudimentary sentiment analysis which we will be doing would be based on Twitter, against a particular brand. And what we will do is we will basically find out whether a sentence is negative or positive. All right. And and then and then summing up all these sentences and figuring out whether the sentiment is going up or down. All right. So that's what we will discuss in case of sentiment analysis. And sentiment analysis is fairly popular popular way of measuring your your company, your brand, or or anything. Okay. So in case of a sentiment analysis, we will be dealing with Twitter, and the way we'll and the crux and the difficult challenge lies in figuring out whether a sentence is positive or negative. Okay, we'll be using a very rudimentary way. So we will take a sentence, okay, and for each word in the sentence we will say 0 for neutral, 1 for negative, and 2 for positive. Each word we will do this way. Okay, and then and then and then we do a summation of all the words. All right, this way we will know if the output is odd, then the sentence is negative. If output is even, then sentence is positive. All right, and then we sum up all these. So we will mark it, we'll put -1 or +1. All right, I'll do it this way. So -1 into the sum and +1 into the sum. Okay, this way we will compute the negative and positive sentiment of the sentences, and we will plot this against we'll plot this against the timeline and against the various brands. Is it clear to you? So if somebody says this was nice, okay, so this is 0, this is 0, and this is 2, which means the whole sentiment is +2. If somebody says this is bad, and this is 0, this is 0, this is minus, this is negative, and since overall is odd, that's why we will make it -1. And that's how we will do the computation of the sentiment of 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 each sentence. All right, so we'll do the computation of the sentiment analysis this way, although this is a very rudimentary way of doing this. If let's say had it been say, let me just try to put something. So had it been not bad, so we have got 1 1, and this time it will become 2 and -2. Okay, no, not 2, this will become +2. All right, so this is a positive sentence because it's an even number, and hence it's a positive sentence. Make sense to you? All right, so this way we could, and the art lies in doing this primitive calculation. This primitive calculation, if it is done over a billion record, it will take a humongous time. Okay, this primitive calculation of doing summation and then doing all of this, it'll take a humongous time if it is done over say 10 billion records. All right, a billion means 9 zeros. And even though this computation is very very rudimentary, but if you have humongous data, you will be able to get very decent output. The cases, the corner cases will be outnumbered by the actual, by the common cases, and overall sentiment will get reflected e- by the popularity. Okay, so, so we'll talk about sentiment analysis in one of the sessions. Would it be more precise to do verb adverb? Definitely, that's Mark's point. So yes, that's correct. If we do more of the analysis of the sentence, so there are many algorithms. So this one is the most simplistic one which we are taking the case. And since it's a simplistic, that's why I've taken the case here. But there are many more algorithms as of today. As Mark is suggesting, can we try to do it verb, adverb, and adjective and figuring out all of them? Yes, definitely. So there are natural language processors which are also available as of today. Every day there is a new algorithm and better algorithm in natural language processing where you can give each sentence to the algorithm and it will tell you how much positive or how much negative is the sentence. All right. So now, and the only downside with using a complex algorithm is even though it might be giving us a good result, but since we are handling a lot of data, if it is not giving us in timely manner, we might have to revert back to a rudimentary approach. All right. There are many other. These were two most popular use cases of big data, where big data plays a very important role. One was sentiment analysis, other was, the recommendation. These were like two basic examples. There are many more complex use cases of big data, starting with fraud detection, cybersecurity, welfare, justice, and probably every aspect as of today. Every aspect could be better augmented with the bigger data, and you will have more insights and better product if you are able to handle big data. Healthcare, life sciences, of course, the whole the whole science depends on the very big data, very huge data. Gene sequencing, healthcare improvements, drug safety, all of these domains have humongous data to deal with. Earlier, the various problems which we thought that a supercomputer will be able to solve, though, in fact, supercomputer could not solve a lot of problems. So it still takes a year of time. Okay, but thanks to the cloud and thanks to the big data innovations, now those problems are easily solvable using multitude of computers parallelly. All right. Now moving on. Any questions still here? All right. Now this chart is showing that there's so many companies using Hadoop and so many companies are using big data as of today, and this is fairly obsolete. As of today, almost every organization is using few instances of Hadoop or few instances of maybe Google Compute Engine. All right, these are few common myths which I keep on encountering. First one is big data means data above or in the range of terabytes. As I gave you an example of map processing, where you have to find the way from one location to another, the map was of say 200 gigabyte size. Okay, but since we demand the result in say few seconds time, as well as the problem is complex, you might have a big data problem. You might have to utilize multitude of computers, and hence you might have to come up with an approach where you can divide the work amongst all these computers. So your data not necessarily have to have the volume. Okay. Now second myth is it's always about social media. The answer is no. The data, it just so happens that the data available from social media is quickly is at a very uh, at a very accessible. It's very much accessible because uh, data sources like Twitter and others, they all provide you data immediately. So it gives you an impression that it's only about social media. No, the as I was talking about my sojourn at InMobi, there I built a recommender based on 200 terabyte of data, and this 200 terabyte of data was basically the Apache logs, our Apache logs. Okay, based on that, we figured out which user likes which game how much, and we gave them recommendations instead of showing them ad, because InMobi shows the ad inside apps. Okay, so it's up to you how you realize, how you figure out that, how you figure out where is the data. And whenever there is data, you can always figure out various kinds of use cases to provide a better insights. Say for example, I was working with a small uh, cab company. They had the GPS location of the driver and the car 24 hours in a city. Okay, so they had this humongous history of all the cars, and based on that, we actually figured out which roads in the city are pretty bad. Okay, and which roads are congested during daytime, which roads are congested during nighttime. So just based on this data, so it's up to you what you can do with the data, and it's not about social media alone. It will replace enterprise data warehousing. The answer is no. So most of the big data naturally have to be stored on multitude of computers. And if something is getting stored on multitude of computers, having a consistency and having a transactional storage is almost impossible. Because the moment you try to enforce the transactions, you will have to have it sequential access to the data, not parallel access to the data to all the nodes. And therefore, it is almost impossible to provide the kind of transactional support enterprise data warehousing provides. That kind of support is not possible using any of the big data tools. Okay. Therefore, when your data is fairly, within few gigabytes or maybe up to 1 terabyte, you might like to use your existing data warehousing solution. Ravi's question is RDMS part of a big data stack? And any comments related to OLTP plus RDMS to the big data. So all of these things actually work together. So EDW or databases or big data solutions, they need to work in conjunction in order to solve your problem. Okay, let's take a case of recommendation, for example. Once you are done with the recommendations, all you will do is you will push these results to your MySQL system from where it will be served to the user. All right, there it will be become a part of the relational data. Okay, so I would put it this way: almost every solution that comes into play, no matter what it is, they have to work in conjunction with existing databases. That does not mean existing database will be called as a big data solution. Okay. For example, at Amazon, we still have the whole catalog in Oracle, while our information of cart, our information about user reviews, user a lot of users statistics, all of that is NoSQL database, is in a database which is running on multitude of computers simultaneously. Okay, that is what we call NoSQL. And so even in case of Amazon, the actual catalog like product title, product attribute, all of that and pricing, all of this information is still lying in Oracle and a relational database. Reason being that there is a lot of information where you require a very strong consistency. In those cases, you should keep the data in your existing database. Right. So for some data, your existing relational database does a better job. For some data, when the data grows bigger than a certain limit beyond which your system can handle, then in those cases you have to move on to a NoSQL. But both of these will coexist. All right. Is a new concept? No. Is a buzzword? No. And will be the future? No, because it's the present. Is expensive? No. Reason being, most of these solutions are open source, which means all the documentations and all the knowledge is available in the wild. Okay. And finding an expert is easier in any kind of a open source solution. Is only for data scientists or is magic? No. Although data scientists are needed, but most of the algorithm which data scientists do is anyway available as part of the libraries. As I talked about Mahat, there we had these libraries containing all the algorithms which you would require. We have enough hardware, we don't need anymore. This is the another excuse. So big data is not about hardware. It's just about the architecture, the way almost all the tools of big data have been designed is that they need to run on commodity hardware. Okay, commodity hardware does not mean cheap hardware. Commodity hardware means a decent computer, and but it doesn't have to be server grade. It doesn't have to be a the kind of blade servers having 100 GB RAM. No, it doesn't have. The other thing is we will build it when we need it. This is another problem because of this psychology, people end up not storing a lot of data, and ultimately when they require the insights, they don't have any data. All right. So that they are mostly into vicious circle. Big data is about Hadoop. Answer is no. There are many solutions which are there around big data solving the same problem. Now, this is a little bit about why it is important for all of us in their career. You can have a look at this slide. It basically shows that there's a lot of demand, and it also shows that salary distribution is higher, which means there's a gap in the demand and supply. Okay, and every year's Gartner's report and Forbes top 10 tech trends clearly indicate a tremendous amount of requirement of these kind of technology in industry. Okay. Rakshit's question is, so metadata should always be stored in RDBMS? Not really, not really. It all depends on what kind of data we are talking about. What do we want out of a particular data? Okay. Metadata is nothing but any sort of data. Okay. Because metadata in actual terms, metadata is also data. So whenever you require a strong consistency, a strong transactional support, you still choose relational database. If you do not require, if you do not require relational database, relational or the consistency support, it's okay to go for a NoSQL database such as HBase, Cassandra, MongoDB, and others. All right. So again, so here the most important part is if your data grows beyond a certain point, you might have to let go of consistency. Consistency as in the strong consistency. All the people seeing the same data at the same time. That's not possible. If somebody tries to make that kind of a consistency, then they will be compromising and they'll be creating bottlenecks. And again, that will be as good as the relational database. Okay. So was he able to answer, Rakshit? Now these are the other solutions available for the big data. Other than big data, Hadoop is the most complete solution out of it because it has everything in a under a single umbrella. And the kind of thing Hadoop provides you, like file system, is something nobody else provides you. Okay. So because when you have to store a lot of unstructured data which you do not want to store in MongoDB or Cassandra, then I mean you want the file system. In those cases, HDFS will do the best job. So there is Cassandra. Cassandra is a database which looks like a relational database, and then there is a MongoDB which looks more like a object storage. Object storage as in the form of JSON. Spark is a compute engine. It does not provide you much of a storage, but it only provides you the is computing. So if you combine Spark and Cassandra, then you will have something storage plus a compute engine. But Hadoop provides you everything, starting with a file system, database, a compute engine, and everything. Okay, and also Spark can be run on top of Hadoop. So things and Cassandra can also run at top of Hadoop. MongoDB can also work in conjunction with Hadoop. So Hadoop becomes a default choice when you want to build a big data platform. Okay. Now Hakim's question is, what is an example of big data that does not need to be RDBMS? Okay. So the reason is, See, the most of the data can be very well classified and organized in RDBMS format, meaning into the tabular format. Okay, even your videos, if you have metadata on videos, that is better. The metadata can be done stored better in a relational format. But if you think about if you think about say your website, which has got a lot of attributes, it has got a title, it has got a product description, under product description it has got further title, it has got lot of complex objects. Okay, now if you try to store this kind of information into a relational database, you will have at least 30 tables which need to be joined in order to produce a single page, right? Now, when you are running in a production environment, a clever thing would be to prepare all these pages and keep them ready to be served. Okay, and that's what the MongoDB kind of solutions do. You prepare the whole page in the form of an object and keep it ready in MongoDB. And when user wants it, you just render it from the MongoDB. Okay. So there are many similar cases where in favor of optimization, you let go of the relational format of your data. You let go of the consistency which you have been always enforcing. Okay. In the favor of the handling the load, in the favor of handling number of concurrent users. All right, so I've got a very good set of questions. Let me try to answer these and then we take a little break. So what is NoSQL? NoSQL is nothing but a database which runs on multiple computers at the same time. MongoDB and Cassandra, HBase are few of the examples. They all run on multitude of computers, and and as an excuse that we can't provide you a SQL, a relational database kind of consistency because we have got this kind of architecture. And that's as an excuse they say that we are no not SQL. Okay, so NoSQL is just you know um, coined word as a Twitter handle. Now people have various completions to it. People some say that NoSQL mean not only SQL, okay, and so on. All right. So Hakeem, I hope I answered your question. Johnny, I hope I answered your question about NoSQL. What is Spark? That's Tim's question. Spark is basically a compute engine similar to a component called MapReduce in Hadoop. Okay. Spark make it possible to do the computation parallelly on using multiple nodes, and it does it really fast by utilizing the RAM as much as it can. Tim's question is why Apache built two of the big data solutions. So Apache did not build anything. Apache is just a license. Okay, it's just people did different people build different solutions. They came under one umbrella and they got adopted by Hadoop. Okay, Apache is more like a license. Cassandra with Hadoop, does it mean for computing with Cassandra persistence? Yes, that's correct. So Cassandra with Hadoop, when I say, so your data is some of your data is lying here. I mean, how should I say? Okay, so Cassandra with Hadoop means the MapReduce, which we are going to run on Hadoop, is going to access the data from Cassandra and then doing it parallelly across the cluster. Okay, data is lying in Cassandra, but the computation is happening on Hadoop. Yes. So in this session, I will devote a full session to Spark, where we will learn about the architect, how to use Spark. Uh, I mean, with the full full one big example, end to end. Okay, so that will be very good introduction, sufficient for you to take it further from that point onwards. If you want to dig deeper, you can dig deeper. Okay. Kamruddin's question is, which type of tools should we use for unstructured data? So unstructured data, okay, let me first describe what is structured data and unstructured data. And structured data is one where we have a clarity of our data to an extent that we know exactly what are the fields in our input, whatever the fields are in our data, and what is the data type of each of these fields. Then we call our data as structured data. We know the clear structure of our data. But in some case, you might not know few information right away. So for example, if you have a CSV file, you know the field, CSV file is comma separated values, and you know the fields, but you don't know the data types, right? And similarly, in case of XML document, you know the fields, but you don't know exact data type. So that is semi-structured data. Third one is unstructured data. In case of unstructured data, we don't even know what are the fields in the input and what are their data types. Example is Apache log or some other kind of format which we need to parse in order to understand it. You need to process it in order to figure out the fields and the data types. So, so which tool should we use for unstructured data? So it all depends on what you want to do with that unstructured data. If you have unstructured data which is lying in the file and you are not able to classify it to in form of fields and their data types, probably a Hadoop distributed file system is the only choice in that case. Okay. Or maybe you can store your big file, big, this kind of data in the form of binary objects inside MongoDB, CouchDB, or other places. But in my personal opinion, if you have got lot of unstructured data, HDFS is the industry's default choice. So Ravi's question is, does Cassandra or MongoDB use Hadoop HDFS file system? Yes, they can use. So there is a library called Mongo Hadoop, okay, which I have put a demonstration on my YouTube channel as well. So that one basically connects the two things together and let MongoDB access the Hadoop as well as Hadoop access the MongoDB, both ways. Okay. Mark's question is, will we work with pulling data from an API into Hadoop Spark to process? Yes. We will be having a full session on Flume and Scoop where we will have a basic understanding on how to bring the data, structured and unstructured data, into Hadoop and outside of the Hadoop. Okay. Now, Kamruddin's question is, if data involves weblogs types of data, if if your data is in the weblog, probably HDFS is your default choice. I said unstructured, not any structured. I said unstructured and semi-structured, half structured. Okay. All right. So now let's take a break of 10 minutes and come back at 10:23. Okay. All right. So I'll answer your question after the break. Till then, you can keep on posting your question or take a break. All right. Hi, I'm back. So, all right. So, I can't see the questions window. All right. So here we are. All right. So let me answer a few more questions. So, are you able to hear me? Great. Great. Now, so Ravi's point is with the recent trend, looks like Spark will replace the MapReduce of Hadoop, but HDFS will exist. Exactly, you are very right. So MapReduce, it may be replaced in certain cases, but in lot of cases, MapReduce will still be there. Reason being, the way MapReduce has been designed is it is for a humongous data set. Okay, far beyond what Spark has been designed for, and good for most of the batch processing. Okay, now Johnny's my question is tomorrow's session, will I get a separate link for the webinar or same link for all classes? For the tomorrow onwards, our sessions will be using another tool called GoToMeeting, where all of you will be able to see each other's question. Okay, and you will get a separate link for that. Right. So yes. All right. So let's go ahead. So in the first half, we discussed the general uh, things like what is big data, why do we talk about it now, what exactly is the problem associated, and what are the benefits, and also what are the various solutions. And one of the solutions is Hadoop. Okay, Hadoop was created by dog cutting of Yahoo and Mike Caffarella. They were basically building a search engine called Nudge, for which they needed to store a lot of data, and that's when they realized that they need to implement the papers published by Google on how do Google manage such humongous amount of storage. And Google thankfully published all those three papers in and all these three papers starting with Google File System, MapReduce, and Bigtable. So based on Google File System, we have HDFS, Hadoop Distributed File System. MapReduce is Hadoop MapReduce, and Google Bigtable is equivalent of HBase of Hadoop. Okay, so the name of Hadoop was given based on the toy elephant of dog cutting's kid, and it is open source, and that has been the most important thing that has mattered, the licensing. If you, because the Apache license is probably the most liberal license which is there in the open. Okay. Why? Because you can start using all of these components in the professional environment and nobody is going to question you. Okay. Any of the Apache license products you can start using as long as you are not selling the core product. Apache license is fairly okay with it. Okay. You can even bundle Apache product, but you cannot specifically charge for Apache, say Apache Server, Apache Tomcat, or Apache Hadoop from your customers. So that is why Hadoop became so popular. The general objective of Hadoop is to be the framework for handling the data and to be the reliable, scalable, and for distributing computing. Okay, for a reliable, scalable, and distributed computing. So, after a point in time, Hadoop became a suite of components, and the basic components start with HDFS, and all the components that lie under the umbrella of Hadoop are basically all the components that lie under a Hadoop umbrella, they all have to be reliable, scalable, and distributed computing. Okay. And it is written in Java so that you can run it everywhere. All right. Now moving on. Now, first and foremost, the most important component is HDFS, Hadoop Distributed File System. So today we are going to discuss the architecture of HDFS. Before that, I need to ask you few questions. It's a fairly technical question, okay? But but the answers, if you think about it, it's actually fairly non-technical. Okay, let me ask you this. Say you are living in a community where you have neighbors and all of you decided that you will build 100 terabyte of data storage in which you will store all the movies and all of your neighbors can watch any movie they want at any point of time. How are you going to build this 100 terabyte of storage so that people can watch and store the movies in it? Anyone? Kumar Saurav's answer is shared folder. Okay, okay. So how will you build that shared folder? So we are talking about 100 terabyte of storage. Johnny says FTP location. Okay. Parmesh says have multiple computers in each home. Okay. Each computer store some data. So all of these people need to keep their computer on all the time, right? Parmesh. Rajiv says in cloud. Mark says in load it all in one drive shared folder. Okay, so you should note that the kind of hard drive that is available as of today is hardly 2 terabyte. Johnny says or maybe SAN. Good, good. SAN means storage area network. Okay, we'll talk about this. We will utilize storage capacity of all residents and access them through the network. Good, good. Tim says buy 25 4 TB each external hard drives, attach it to one servers and share. Okay. Mark suggests that buy Microsoft's OneDrive Unlimited and free with 365 account and open API for REST calls. Okay, so but if you put movies over there, every time you have to watch a movie, it is going to take a long time to download and watch, right? Good, good, very good answers. Now, this was the typical way we build this kind of storage. We call them, some call it network attached storage, some call it storage area network. Although the vendors are different, the design is a bit different, the kind of reliability is little bit different in both. Okay, so but the principle is same. The principle is same. All you do is buy, say, 100 hard disk, 1 terabyte each, and then connect these 100 terabyte these 100 hard disks to various computers. Maybe you buy 25 computers, and on each computer you attach four hard disk each, and then you bring all these 25 computers to the network, and then you map these drives as a folder under a particular folder. Okay, you can map each hard disk as a folder. Okay, so to the user, they will see that there are 100 folders, 100 subfolders under this folder, and they can start storing the movies. So do you see any problem with this approach? Kamruddin says it's good. Do you see any problems with this? Yeah. Pamesh says, in case one computer switches off, the data cannot be available to others. Good. Very good. Duplication. That's Eric's point. So how exactly? I need to understand that. Do you mean replication? Duplication? I mean, do you mean replication? There has to be copy of the data. Johnny says it's complex and expensive. Okay. I would say that it's expensive, though it's not that complex. All right. Pamesh says data crash. Kamruddin says we have to go for replication. Yes, that is right. Tahar says need to search each drive to find the data. That is correct. Eric says meaning there is no metadata to define which movie is where. Good point. And if you don't duplicate data across drive, you cannot lose. You can lose the data. Very good. Very good. So Eric's point is that there is no way right now. The problem is where is which movie. Either we define conventions saying drive 1 contains all the movies starting with A, drive 2 contains movie with B, and so on. Right? Any other problems do you see? Yes. Copy over 10 GB over network could become slow. Specifically, several people are trying to download at the same time. Excellent point, Tim. I was just waiting for this. Right. So Tim's point is that if all the there is a new movie, there's a new movie in the network, and all the people want to watch the same movie, and if all of them are hitting the same hard drive, then which means that the computer will get overloaded, and none of the people will be able to watch. Right, right. Yes, that's correct, Parmesh. In case we form this kind of thing, that movies are stored, A alphabet movies are in drive one and so on, there are chances that we'll waste a lot of disk space, as well as we will also. Basically, it will be a data uniformity problem. All right. Now, here we. So, these are the challenges with this one. Okay. First, failovers are not immediately available. Although we might build a backup, as in on the same computer, we could build a RAID 1 where every data is duplicated twice. But in case the network connection get lost, if the computer goes down completely, then there is no failover. Second is data distribution uniformity. As you have raised, some of the nodes will be very highly busy and some of the nodes will be very scarcely busy. Is it best value for money? Because we bought new hard disk, couldn't we utilize our existing hardware? Now, what about increasing accessibility? Meaning, one movie, e- everybody wants to watch a particular movie, and that will overload one computer while other computers are fairly free. Scaling out as in today we have these many computers, we have built some sort of a plan, but tomorrow we want to increase the capacity to 120 terabyte. So, is our plan, you know, will this be able to tolerate a kind of expansion? Of course, no, because we have built already A for this drive, B for this drive, and so on. We'll have to rearrange everything. All right. So the solution is, for these kind of scenarios, if you are planning to store a data of 100 terabyte and onwards, HDFS will be a better solution because it caters to all of these problems. It caters to all of these problems. All right. So a little bit about the architecture of HDFS. HDFS is made up of metadata, metadata node or admin node or name node. Name node basically stores what is where. As some of you have already said, there should be some kind of a metadata information which serves like an index. If somebody says, "Give me this movie," it should know where is this movie. Okay, so that is admin node. And there is something called data nodes. Admin node is singular. There is only one admin node in the network, while there are multiple data nodes in the network. There are multiple data nodes in the network. All right. Okay, so before proceeding, looks like there are many questions asked. Could movies be striped across the drives? Good, good. So we will talk about this now. That is Eric's question. What is the admin node crash? Isn't it the bottleneck? Okay. So all right. Now we have here, we will talk about both of those points, Eric, in a minute. Okay. So we have multiple data nodes and there is an admin node. Data nodes store the actual data, the content which is inside your files, while the name of the file, the name of the folder, and attributes of the file are stored at admin node. An admin node knows which data node contains which file. Next is these files are split into a block of 128 MB each. Earlier it was 64, now it is 128. Okay. Why? Because this helps fitting big files onto small hard disks. Second, it leaves less unused spaces on the disk. Fourth, it optimizes the file transfer a- and it distributes the load to multiple machines. Okay. We'll talk about how it distributes later. All right. So this is how the HDFS is able to provide a lot of features which were missing in our design. Okay. Now next is that each block, a block of 128 MB eh, is sliced, and each block is basically replicated 3 times. This number 3 is called replication factor. The default value of a replication factor is 3, and you can change replication factor per file basis. Important file, you can change it to maybe 5, meaning each block of a file will be copied that many times. If you have replication factor of 3, that means each block will have 3 copies, and also that means that it will consume 3 times of memory, 3 times of disk, not memory, 3 times of the disk. Now, and these replica block are always on the another node instead of the same node. Okay, there is no possibility that two blocks which are copy of each other will be on the same machine. All right. So this is how. Next question, next design concern is the name node. The impression it gives you is the user will come and talk to name node, and name node will gather data from data nodes and give back to the user. But in reality, this is what happens. The user comes to the client library goes to the name node, and name node just hand over the information to client library, saying that read the data directly from the data node. Do not bother me. Name node does not all requests are not routed to the name node. Name node just gives the information to the client saying go to the data node and read the data by yourself. Okay, this way the name node keeps itself fairly free. Even the replication of the blocks happen amongst the data node themselves. Okay, name node just informs each of these data nodes to copy the block in order to maintain the replication. All right. Now let me take the questions now. Do you have any questions now? Okay. What if admin node crashes? That's a common question. So first, Up to Hadoop 1.0, there used to be a bad mechanism. The if admin node crashes, you have to manually bring it up. Okay, but now there is something called secondary name node, which you can bring up immediately, and that too is highly available, in the sense that secondary name node can be kept in a passive mode, meaning it is it is not active, but it is having all the information that admin node has, and the moment admin node goes down, it will come alive. Okay, that's how it a lot of problems could be avoided. Okay, all right. Mark's point is, oh, it's like this is like IBM's horizontal processing, and 64 MB in from actual storage. Each data node holds 4 MB. No, each data node will have 128 MB minimum, because block size is minimum 128 MB. Johnny, I did not get your question. 128 million blocks? No, 128 megabytes. Okay, each block size is 128 megabytes. Does it mean that 100 terabyte movie need 300 terabyte storage? That's Tim's question. Yes, you are right. 100 terabyte movie storage will require 300 TB storage. Okay, if you are keeping a replication factor of 3. But in case of movies, we know that it's not very critical data, so we can bring the replication factor down to 2. Okay, which means 200 terabyte of storage will be wasted. Why is why so let me rephrase Hakim's question. Why is a block replicated on the on different nodes? Why isn't it duplicated on the same node? Reason being that most of the failures are not are due to the hardware failures, so it's better to keep a backup somewhere else than keeping on the same node. Okay, it's more safer. Do the data node communicate between themselves? Of course, yes. The replication happens because the node communicates between themselves. Name node knows that this is the data node which contains the block and need to be copied somewhere else. Okay. All right. Now, other important aspect which I forgot to mention, in case one of the data node fails, so the moment a data node fails, all the blocks on that data node will get lost, which means the replication factor of those blocks which got lost have come down to say 2 from 3. Okay, though their copies are available somewhere else. Now, if that happens, if a data node get lost, all the blocks that got lost because of that data node, name node quickly builds up, quickly start copying those blocks in order to bring up the replication factor to 3 again. Okay, Eric's question is, can name node also be a data node or vice versa? Yes, of course. So when we say data node, admin node, basically these are processes, like I mean these are these processes, these are the operating systems processes, this is the software, and these processes are running on a particular port, listening on a particular port. So you can have all of them running on the same machine. They have a different ports to block. Okay. But it does not make any sense to run two data nodes on the same machine, as well as it does not make any sense to try to overload our admin node with the data node, because admin node is anyway very busy. Okay, so it generally makes sense to have these separated. Okay, Kamruddin's question is the secondary name node updated continuously? Very good question. So we talked about a secondary node, which is an identical copy of admin node. The moment admin node goes down, secondary name node takes its place. All right. Now, the way it happens, how is secondary name node always alive, always fresh? How does it happen? The reason is every time admin node is changed, every time you create a folder, you upload a file, admin node will inform the secondary node, as well as data nodes will inform admin node as well as secondary node with the information. Therefore, for each data node informs both admin node as well as secondary node. Okay. So Tim, yes. So a 100 terabyte movie needs 300 TB storage if you have a replication factor 3. Okay. All right. Okay. Hi Sergio, you are actually pretty late. And Johnny's question is, are these all in cloud or company has to build it internally? Okay. So yes, all of these are internal because okay, and it's up to you how you want to keep it. Say for example, in case of no big data, what we have done is we have taken servers from a third party and installed Hadoop on top of those servers and made it available to all our students. Okay, so most of the organizations do it this way. They buy servers from various companies, and then they install their software on top of it, and then make it available to their employees and other people. Okay. Now Kamruddin's question is the secondary name node updated continuously to keep it consistent with primary name node? Yes, that's correct. Rajiv question is there can be multiple admin nodes? No, there could be only one admin node at a time. Otherwise, there will be too much of inconsistency in the data. So Mark's question is, will we cover connecting different computers to be usable for different data nodes? So we'll not be covering the administration part in this session. We'll be just covering a overview on how to set up a cluster. That too on a very I mean very theoretical level. It will not be a hands-on installation exercise. That will be in our administration session. Now, Eric's question is, can we have multiple active name node and load balancer? No, that's a design part of SDFS. Admin node makes sure that there is a single point of information, and also make sure that consistency is strongly maintained, because the moment you have multiple admin node, there will be multiple nodes having the metadata, and you'll have to keep on synchronizing them, and that synchronization might take time, and therefore some of the users will might get an older view. So in the favor of strong consistency, admin node is kept single. Kamruddin's question is, do the data node communicate among themselves? So data node can communicate among themselves, but the most of the communication is started by admin node. Admin node might direct data node 1 to start copying some of the blocks from data node 2. How long does it typically take to load 1 terabyte data into HDFS? Okay, so it all depends on what kind of network do you have, and what kind of basically how far is basically it basically depends on the bandwidth. All right, but copying 1 terabyte data locally, it takes around 14 hours with a very good USB connection over USB. And 1 petabyte, I have no clue. How is data update handled? Now, each of the block is write ahead. HDFS is a write ahead, I mean, write only kind of a file system. If you are basically changing a file, you are creating new set of blocks. Okay, an old set of blocks will be deleted. Rajiv's question is data node have some limit? So data nodes limit is basically defined by hardware terms, and based on how much storage is available locally, that is its limit. Okay, so Rakshit's question is meaning, if there is a change in data, how does data get updated to all new nodes? Okay, so when you are creating a file, you inform name node that, hey, I want to I want to create this file. Name node will create an uh, empty I mean, name node will make an entry saying that this file is being created. Okay, and then, okay, let me just go through one example. Okay, Rakshit, I'll just go through an example, and then I'll believe I'll be able to answer your question better. Ravi's question is, with respect to deleting old records, does the new ones go to the same data node? No, I don't get that. Your point. So, okay, please rephrase your question because I'm not able to figure it out. Till then point of time, let me just you know go take you through this. Okay, so HDFS client comes in, creates a file. The first step is it goes to it. HDFS client asks the HDFS to create the file. Then request goes to the name node. Name node makes an entry, and then the third step is that it starts writing the data to data node by opening output stream called fs data stream. So HDFS client starts writing to the data node. At the same time, data node will start copying the data, these blocks, to the other machines. Okay. Now question comes in, who creates these blocks? The block creation duties of HDFS client. HDFS client it will while writing it will write in terms of blocks. Okay. So when HDFS client went to name node and name node created an entry saying that somebody is trying to create this file. Okay. So that if somebody else at the same time comes and tries to create the same file, name node will not let them do it. Okay. And once HDFS client informs name node that, hey, I'm done with writing my data, you can update your metadata. So name node will mark it that this file has been successfully created. Okay. And the similar way, when HDFS client comes in to read a file, the first thing it would do is it will go to the name node. Name node will tell the client that for this file, these are the data nodes, and on each data node, these are the blocks stored. Now you can read whatever block you want to from these data nodes. Okay. Now let me take up the questions. Good. This time I've got very good questions. And let me just read the questions once. All right. So Ravi's question is, since it is write only, does the update for the same record happens in the same data node? Generally yes, but it is not necessary that way. It is basically decided by name node based on how much space is available where. Kamruddin says, is the data node sends any sort of acknowledgement to the name node for the replication completed? Yes. So data node, as soon as the replication completes, it keeps an informing name node. Okay. Who manages adding of the new update and deleting the old records? So generally, all of that is managed by the client library itself. Okay. Client library is informed by name node that to modify this file will be abandoning these records, these blocks, and will be creating new one. Okay. So name node at one end will just drop the metadata and will mark it free, although the actual data might be lying in the data node, just like in a hard disk. The actual links are removed from the file header. Okay, file system header. And similar way, if name node just drops that saying this file has no blocks, that means um, the file is deleted. All right. So while uh, making an update, it's basically creation of new set of blocks and abandoning the older blocks. That's all. All right. So what does name node contain? Name node contains the entire metadata into the memory, and it also has a copy of whole memory into the disk. In case the computer shuts down, there is always a full copy available in the disk. Okay. The metadata contains list of files along with their folder structure, list of blocks for each of the file. Okay. So say for example, if you are trying to store a file called data, okay, He'll create a folder. It will have all of this information. It has got part 0, replication factor is 2, and these are the nodes which contain this particular part. All right, and so on. The file attribute, access time, etc. is part of the metadata, though the transaction log is stored into the disk. Okay, transaction log is not retained in the memory while rest of the metadata is in the memory. Now you might argue that why is it that we are keeping all of this metadata in the memory? The reason is name node needs to free itself as much as it can. Name node needs to keep itself free as much as possible. That is why it needs to respond really quickly, and for that it needs to read the data really fast, and that is why the data is kept in the memory. All right, so slide number 42 is the standard slide. Yes, I have purposefully skipped it because the other slides have same thing information. All right, so basically a client comes to the name node queries for the file which is the client looking for, and then the information is returned to the client. Now client directly goes to the data node, starts reading the data, and that's all. So name node cannot be commodity computer. I guess it has to be server grade. That's correct. So generally the way name node is chosen is something like a 32 GB RAM. Okay. So that it can store a lot of files and lot of blocks. So generally name node has to have a huge memory as compared to the normal commodity hardware. That's the only thing uh, you know which is the requirement. So you can say that name node is generally a high-end machine, not a lower-end machine. All right. So now going back to the diagram. So this was a description of Hadoop distributed file system. On top of Hadoop distributed file system, there are many things as part of the ecosystem of Hadoop. There is something called Yarn. Yarn is a compute engine that makes it possible to take the code to the data. So yeah, on Yarn, when you want to execute something, it takes your computation to near the data which is on your data node and get it done there rather than bringing the data to the code. All right, so Yarn basically makes it possible to run your code parallelly on multiple machines. And the way you instruct Yarn is either via MapReduce, that is a paradigm, or by the way of using Spark or other kind of tools. Okay, so most of the computation happens using MapReduce. All right, and for that MapReduce uses Yarn internally. If you want to have some sort of structured data which need to be updated very frequently, you would like to go for HBase. Okay, HBase is a NoSQL database which provides you the ability to store data in tabular format. If you want to do the computation on top of HBase, you will have to utilize MapReduce because HBase does not provide you any kind of SQL query language. If you want to do SQL on top of HBase, you might like to go for Hive. Hive is nothing but a, a converter from SQL to MapReduce. So you whatever data you want to churn, you use Hive to run the SQL queries, which get internally converted into MapReduce. Now, some people realize that for a distributed computing, SQL is not doing the justice because it was not designed for SQL. The SQL was not designed for distributed computing. That is why some people invented a tool called Pig, and the language is called Pig Latin, which is very similar to SQL and is very simple. The next component is Mahat. Mahat is basically a machine learning library containing most of the algorithms which can be executed. So Mahat is basically a machine learning library. Okay, it has all the algorithms listed. Okay, and here at the bottom of the pyramid, you can see the Flume and Scoop. Using Flume, you import the data from other sources onto HDFS, and using Scoop, you import and export the data from the relational database. Using Scoop, you can push the data into HBase or Hive or or into the HDFS and vice versa. All right. Now, if you can if you think a little about what's going on, you have these many components for different objective. Now, if you have a big project in which, say, you have to do a computation of recommendation, okay, for computation of recommendations, you might have to download a lot of data, copy a data from your websites, your logs and other stuff, churn that and clearly prepare the data which needs to be fed to Mahat. Okay, and once you have done that, you will have to execute Mahat to get the output. So you will understand there are at least 10 to 15 different steps which will be required in a project, and therefore there has to be a tool similar to Apache Ant or Make which can stitch these things together, okay, which can do the workflow. When my import finish, then execute this. Once that part is executed, then run my SQL queries and so on. Okay, so to tie things together, we use a workflow called Uzi. We prepare our whole workflow in Uzi and we just keep running our Uzi again and again in order to get the results every night. Okay, now let me look at your questions. Wow, now this time there are good questions. Now, Kamruddin's question is how the load balancing is done in data node when one data node is catering to many clients whereas other is not. Okay, so Kamruddin's question is that we talked about our file system and we said that this our design HDFS will cater to load balance, but how? Okay, let me take a step back. Let me take a step back here. When we said that data is split into the blocks and these blocks are replicated, which means one particular file is located on multiple computers first, which means If there is a file which is in high in demand, the whole cluster is busy. All right? Whole cluster is busy, not only one. Second, when you are duplicating the data, when you are duplicating the blocks, which means for each block there are three sources of data, and hence the availability becomes three times. So even if your file is single block, if your file is say 100 MB and it has only a single block, still there will be three computers that will be used to store the data and hence serve that block. And in case you have got further demand and more computers, all you need to do is, for time being, for few months, all you do is increase for a month, you just increase the number of replication, you increase the replication factor by to say 5 or to say 10. That means it become your data is available on 10 different nodes, and 10 different nodes can cater to the high demand of the use. All right, I hope I answered your question. Mark's question is, can you command Spark via Yarn 2? Also, can you exchange HBase for Cassandra? All right, that's a good question. Now, let me answer first. Going back to the diagram, here, here, Spark does not do what Yarn does. Spark does the computing, but it requires some sort of a manager for the resources, and Yarn is that manager which can help it. So Spark basically runs either on Yarn, or it uses something called mesos, or runs in local mode. Okay, now regarding your second question, can we exchange HBase for Cassandra? That I'm not sure of, although some places mention that the Cassandra can run on HDFS, but I'm not sure about it. Spark's output is exposed via HBase, so Spark can write anywhere. So while churning the data, we can specifically tell store this data set into HDFS or into some other file system. Spark can store in lot of different kind of a file systems or databases. Rakshit's question is, can you explain Yarn again, please? Okay, Yarn here is a resource allocator, meaning if you want to run a process, we tell Yarn, can you run this process on this particular node? And Yarn will do that. Okay. Or if you want to execute a piece of code, we tell Yarn, can you execute this piece of code on these nodes? Okay. That's what Yarn does. Eric's question is, does HBase communicate with Spark? Yeah, Spark does communicate with HBase and HDFS. Eric's next question is, can Flume ingest semi-structured data? Yes, because Flume has a concept of defining, customizing the data types. So whatever data you want to store, you can store using Flume. Yes. So like service bus messages, of course, Flume can handle all of that. Okay, Kamruddin's question is, How the load balance is done in data node when data node is getting okay. Yep. Name node definitely make sure that the load is balanced between various data nodes. Name node makes sure that if it has given the if, if there are too much of demand, if one particular data node is too busy in catering some other, it will transfer the load to another data node. So first five requests came for the same file. As soon as first request came, data node noted down, name node noted down that this particular data node is busy because name node has recently given information about that data node. And as soon as that happens, the next read request, name node will try to redirect to another data nodes. All right. Ravi's question is, my understanding is Hadoop is for computing and persistence. Is Yarn for both or only for computing? So Yarn is a part of Hadoop. Okay. Earlier, MapReduce and the basic computation was in a single unit called MapReduce, but later on it was divided into two. So half of the part of the Hadoop is actually Yarn. All right. Johnny's question is, are there any other tools like Yarn? I'm not sure about it. The other tools, other comparative tools is Mesos, which is a resource manager. All right. Now, Cloud Labs. Okay. So those who have already enrolled and are our student, please go through our this console. Okay. And also the login password to the cloud is available in the learning management and under session 1 and in installation guide. All right. Now Ambari is something which basically helps you administer the cluster. Okay. If you are setting up your cluster, you can use Ambari to monitor your cluster. Okay. Here, say tomorrow I want to add one more node. I can do I can do that easily. I can go to host and say add one more host and so on. Okay. So basically Ambari helps you installing, provisioning and controlling your network. All right. Here it shows that this Uzi service is down and HBase is running fine. There are some problems with, there are no problems with Hive. Yarn is also running perfectly fine. In case of HDFS, our secondary name node is down. I have shut it down purposefully. Okay, and Zookeeper is running. So basically, Ambari is to see what's going on. Now there is Hue. Using Hue, you can interact with various kinds of services. For example, if you want to do something inside the file browser, this is our HDFS. Okay, this is our HDFS. Please create your own separate folder before you start uh, working on this. Okay, and you can interact with various services using Hue, which runs on 8000 port, while Ambari runs on 8080 port. Okay, and to execute pig query you can use this and so on. All right. Next is you can connect to SSH, connect to these any of these Hadoop servers. We have 4 5 servers, and you can connect to any of them using SSH or PuTTY in case you are using Windows. Also, go through your courses, finish the quiz available in the session. Okay, finish that quiz. And if you want to set up your virtual machine, you are free to do so. We have given those details in the installation guide. Okay. Sarju's question is how Mahat plays a role here. Mahat is a collection of library. If you want to generate recommendations, if you want to group items together, those kind of machine learning kind of jobs are done by Mahat. Mahat is basically the overall objective of most of the churning of the data. At the end of day, you will run Mahat algorithm on top of your data to generate the results. Johnny's question is, can we use MongoDB instead of HBase? Not really, but in case you want interoperability, you can use a tool called Mongo Hadoop, which makes that possible. What is Tez? Tez is also one component. Okay, and although Tez we are not covering, and Tez is, Tez is something which I'm not covering. All right, it's a all right. Now, so Tez is also one such component, and yeah. Also, those who have not signed up, they can sign up from the website. They can enroll for the course. And if you have any doubts, just feel free to ping me. This is my phone number. And if you want to drop us an email, you can drop us an email at this. All right. So, any other questions for me? Great. Thank you, Mark. If you found me awesome, I'm pretty happy. And so, link for what, Johnny? The video, you mean? So if you have signed up for the course, you will get the link before half an hour. Okay, before half an hour the session start, you will get the link. All right. If you are enrolled for the course, then you will get the link 30 minutes prior to the session start. All right. So if you have any questions, feel free to reach us at knowbigdata.com, and this is my phone number. Feel free to, if you have any doubt, just feel free to call me up. All right. So that's pretty much from my side. So Feng, if you go into, I'll show you. Can you see my screen? If you go into my courses, if you click on my courses and then click on the course, and under session 1, there is something called installation instruction. Can you see this? So inside that, you will find the login password for the Cloud Labs. Open this document, you'll find the login is student and there will be password inside it. All right, I'm not telling here because that'll get recorded. All right. So any other questions for me? So rest of the course is paid. The session one was free for all. Okay then. Great. All right then. Great. See you tomorrow. If you want to enroll, you can go to the main website here. Okay. www.knowbigdata and go to the course, and then you can just click on enroll and you can enroll. All right. It'll show you if you go to the website, it will show you the uh, different time. I mean, this time in your local time zone. See you tomorrow then. Have a good day. All right. Thank you, Rajiv. Thank you, Juan. Yeah, this is 3 hours only, right? So that's why we finished. That's pretty much. Have a good day and see you tomorrow then. Bye bye. Okay, so Juan, did you join only 1 hour ago? Not really. The whole class was 3 hours today, and we started around 8:30, which was 3 hours ago. I did not get the question. Oh, oh. So time zone issues basically you're facing. All right. So tomorrow, just reminded that from now, it'll start. It'll end at this, and it'll start 3 hours before this time. Okay. Just make sure that part. All right. Thank you very much. Have a good day. Bye bye. It's up to you to set up the virtual machine, but what you can do is you can you can basically log into your account and go through the installation instruction. Okay, go through the installation instruction and use the cloud labs. So I'll be sending the video recording in say half an hour time, then you can go through the video. Okay. All right, thank you, Suresh. All right. Thank you very much. Have a good day. Bye bye. Bye bye. Bye bye, Eric. Bye bye, Fang. Bye bye, Kamruddin. Have a good day.